Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is 5.8, which is inverse trig functions and integration. All right. So first, let's recall something. Recall that the derivative with respect to x of sine inverse of x is 1 over the square root of 1 minus x squared. Similarly, the derivative with respect to x of cosine inverse of x is 1 over, negative 1 over the square root of 1 minus x squared. All right. Now, if you don't recall that, let's see why this is true. All right. So how? Well, consider this. Let's say that I have y equals sine inverse of x, right? And I'm looking for the derivative, so I'm looking for dy dx. What I can say here is if I take cosine of both sides, I end up with, if I take sine of both sides, I end up with sine of y is equal to x. If I take the derivative of both sides here, well, on the right side, it's easy. The derivative of x is just 1. On the left side, the derivative of sine of y, well, that would be cosine of y times dy dx by implicit differentiation. From there, we would then say that dy dx is equal to 1 over cosine of y. But now, let's think about cosine theta in general. So we know that there's this identity, sine squared plus cosine squared is equal to 1. Solving for cosine here, I end up with cosine theta is equal to plus or minus the square root of 1 minus sine squared theta, right? If I just consider the positive version here, well, I end up with, well, cosine of y would be 1 over, 1 over cosine of y would be 1 over the square root of 1 minus sine squared of y. But if we look at this line up here, that told us that sine of y was just x. So what we have here really is just 1 over the square root of 1 minus x squared. So therefore, if I start with y equals sine inverse of y, then dy dx is 1 over the square root of 1 minus x squared. All right. Now that is for sine inverse. For cosine inverse, it is very, very much the same idea. All right. Um, so now that is the derivative of sine inverse and the derivative of cosine inverse. But that's Calc 1 stuff. We're in Calc 2. So let's do the integral of some of these things. And in here, what we're actually going to be talking about is the integral of what we had here on the right, the integrals of things like that. All right. So, theorem. And this is integrals involving inverse trig. All right. So let u be a differentiable uh, function of x. And let a be greater than 0. All right. We have these three um, properties. The integral of du over the square root of a squared minus u squared is equal to arcsine of u over a plus c. Remember, arcsine is the same thing as saying sine inverse. So arcsine of x is equal to sine inverse of x. All right. If I have the integral of du over a squared plus u squared. This gives me arctan, right? Excuse me, 1 over a arctan of u over a plus c, right? And finally, if I take the integral of du over u times the square root of u squared minus a squared, that's going to be 1 over a arcsecant of the absolute value of u over a plus c. All right. So these are just three integrals that you really should memorize. Now, let's do some examples to see how these would be applied. So here we're using the instructions overall are going to be just integrate or evaluate the integral, right? So here we go. We have the integral of dx over the square root of 16 minus x squared, all right? You know what? I'm going to rewrite this. I'm going to rewrite this as 1 over that times dx. There we go. Same exact thing, right? Now, what I want you to notice here is that I have a difference of squares in there. This difference of squares is what gives away what I should be using. Because let's look at these three. I have a difference of squares, I have a sum of squares, and I have a difference of squares. So because it's a difference of squares, I'm either going to be working with the first version or the last version. But now, let's look at what we have, right? In this first version, we had constant minus function. In the second version, we had function minus constant. Which one do we have? Well, we have constant minus function. So therefore, I know I'm going to be working with that very first integral. So I'm going to rewrite this now as the integral. Oh, how did you do that? Okay. The integral of 1 over the square root of 4 squared minus x squared dx, right? And at that point, it's perfectly in the format of that first integral. So look at the places of a and u, all right? A is 4, u is x. So what's going to give me is arcsine of u over a. So in this case, it's going to be, I'll write it as sine inverse of u, which was just x, over a, which was just 4, and then that plus c. All right. Next one. So that was a. B. In B, we're going to say, well, let's take the integral of dx. Well, I don't want to write it that way. 1 over 6 plus 25x squared dx. Now in here, what gives away what I should be doing is the fact that I've got a plus, right? I've got a quadratic there with a plus. That second notation there, I mean the second integral is the one we're going to be doing, the one that involves arctan, because I've got that plus sign of a quadratic down there. All right, so what we're going to say here, well, let's rewrite this. This is going to be the same thing as saying the integral of 1 over the square root of 6 squared plus 5x quantity squared dx. And look at that. Now it's perfectly in the same format. A squared plus u squared on the bottom. All right. So now I can go ahead and apply my formula for arctan. So I have, well, in here, let's just say that this is RA, this is RU, right? And remember, it became arctan of 1 over A, excuse me, 1 over A arctan of U over A. But before we continue, let's figure something out here. Look at what we have in this equation. This is our U, and on top I've got du, right? This is our U, on top I've got du. Let's look at ours. This is our U, right? And on top I've got 1 dx. But if U is equal to 5x, then du would be 5 dx. So what we actually have here is we must account for that. We don't have this 5 in the original problem, all right? In the actual formula, the numerator, that's all du. So it depends on what u is, right? So we don't have that du as written in this problem. So we're gonna need to manipulate this a little bit. So since u is equal to 5 dx, then du is equal to 5 dx, right? Now what I can do there essentially is just treat this as a u substitution where dx is going to be equal to du over 5, right? At that point, what we can do is we can rewrite this integral as the integral of 1 over this square root of 6 is still there, squared. This 5x, that's our u, so I have plus u squared. And this dx was du over 5. In other words, it's 1/5 times that integral. I won't rewrite it there. I'll just shift it. So, in other words, we said it was 1/5 times that integral. And now it's actually in the format that we wanted it, right? Now it's in the format that we want it in because we've got that integral just being our a squared plus u squared, and on top having the du. That constant in the front, no longer need to worry about that. So what we're going to get now is, well, we have that 1/5 from the constant in the front, and then we said it was 1 over a, so 1 over the square root of 6 times arctan of u over a, so u over radical 6. And then all of that plus c, right? Rationalizing that a little bit. You know what? I won't rationalize it, but I will change the value of u. So my final answer, I'll write it as 1 over 5 radical 6 times tan inverse of, what was our u? 5x. So 5x over radical 6, and all of this plus c. I'll leave our final answer as that. All right, we just have to make sure that our final answer is definitely in terms of x. Next one. All right, so that was B. C. So if I have the integral of 1 over x times the square root of 9x squared minus 4 dx. All right, so in here, let's look at what we have. We have a minus. We had two options for that, but we've got the function first and then the constant. So that is scenario 3 down here. All right, the constant first, the function first and then the constant. And well, let's see what we have here. This 9x squared, we can rewrite it. So we can have the integral of 1 over x times the square root of 3x quantity squared minus 2 squared, and all of this dx, right? And now let's look at what we have here. In here, our u would be 3x. So therefore, our du would be 3 dx. And we arrive at the same problem as before. Let's look at the generic form over here. All right. Well, first of all, there's a u here and a u there. And also up here is du, right? So if our u was 3x, we're missing a 3dx up here somewhere. We're also missing a 3 down here, all right, because this needs to be our whole function u. So let's just continue to manipulate this. So what we're going to say here is let dx be equal to du over 3, all right, and there all I did was solve for dx just like we would with any u substitution. And now we end up with, well, the integral of 1 over, well, this x, I didn't use it for my substitution, so it's still out here. X times the square root of this 3x, that was my substitution, so I've got u squared minus 2 squared, and then this dx, that became du over 3. But now, let's look at that 3 and that x. If I combine those, I mean, it's multiplication, right? So if I multiply 3 and x and 3, that would give me 3x, which is just u. So what I really have here is the integral of 1 over u times the square root of u squared minus 2 squared du. And now we can go ahead and apply that formula. So what we're going to get here is 1 over a, our a is 2, so 1/2 times arcsecant of the absolute value of u over a, which again was 2, plus c. But then we say the problem wasn't about u, right? The problem is never about u. So it's 1/2 arcsecant of the absolute value of 3x, and then all of this over 2 plus c, all right? But again, we ran into the same issue as we did in the previous problem, right? We cannot just go ahead and start applying the formulas unless we're sure that we have the du required in the problem, all right? So again, in example B, we were missing that du because we didn't have that 5dx. In example C, we did not have that 3dx, right? So I recommend that you treat this as a regular u substitution to put it into the exact format. All right, so that was example C. Let's do example D. And here we go. So D is going to be the integral of dx over the square root of e to the 2x minus 1. And I'll just write this a little bit differently. I'll move the dx on the outside. So 1 over the square root of e to the 2x minus 1. All right, so in here, let's think about this one. All right, I've got e to the 2x minus 1. So the first thing I'm going to do here is I'm going to rewrite this. I'm going to rewrite this as the integral of 1 over the square root of e to the x squared minus 1 dx. All right, and I've got a minus here, so it kind of gives me an idea of which of the three things I'm going to be using, right? And specifically because I've got a function minus a number, I know that I'm going to be looking at, where is it? At that third scenario because I've got a function minus a number. So we need to manipulate the integral to look something like that. All right, so let's continue manipulating this. So in there, well, they want me to erase that e. All right. So in here, I'm going to say, well, u would have to be e to the x, right? To have that function minus a number pattern. So du would be e to the x dx. So therefore, dx would be du over e to the x. But e to the x was just u, so it's really du over u. All right, let's see how that affects our integral now. So what we're going to get now is the integral of 1 over the square root of e to the x. That was our u. So we have u squared minus 1 times dx. dx was du over u. So look at that. We actually have, we can rewrite this as 1 over u times the square root of u squared minus 1 du, which is the exact format that we needed, right, for that third one. So what we can say now is that this becomes just, well, our a is 1, right, because 1 is just 1 squared. So maybe I'll leave it at that. 1 is just 1 squared, so our a is 1. So this becomes 1 over a, so 1 over 1, times arcsecant of the absolute value of u plus c, which means arcsecant of the absolute value of e to the x plus c. But e to the x is always positive, so we can just rewrite this as arcsecant of e to the x without the absolute value, all right? Because e to the x is never negative. All right, so again, the idea with these is you need to write it in the specific format, right? You need to make sure that you have everything that you need in order to be able to use those three integrals, all right? Those three integrals right there. We want to make sure that we have it in these specific formats, that we're not missing anything, all right? The constant a could be whatever it wants to be. The function u can be whatever it wants to be, but we have to make sure that wherever u shows up, it actually is there. So we have du in the numerator, we have to make sure that we have that, all right? So let's do more examples. So that was D. E. E is the integral of 1 over, let's get it as x squared minus 6x plus 12 dx. All right. So as written, this doesn't really follow any of the things that we wrote, any of the formats that we had above. All right. But doesn't mean that we can't solve this. All right. What I'm going to do here is I'm going to manipulate this. All right. Again, a lot of this is going to be manipulation. We want to manipulate our functions algebraically in order to write them in a different format. So let's do something called completing the square. All right. So complete the square. So here's what we've got. We've got x squared minus 6x plus 12. All right. And I'm going to complete the square on that. Well, how do we complete the square? Well, we're going to take half the value of that negative 6 and square it and use it to add 0. Let's write down everything I just said. So we're going to take that negative 6, then we're going to divide it by 2, then we're going to square it, and then we're going to use it to add 0. All right, because remember, adding 0 doesn't change anything. So I'm taking negative 6 divided by 2, so that's negative 3. Square it is positive 9. And I'm going to use that positive 9 to add 0. So what we have here is x squared minus 6x, and now I'm going to add my 0. Plus 9 minus 9, that's adding 0, and that plus 12. So at that point, I regroup them. I'm going to combine the first 3 and factor it, right? So if I factor those, I end up with x minus 3 quantity squared. And then if I combine like terms on the rest, I end up with just plus 3, right? Negative 9 plus 12 is a positive 3. So what this tells me now is that the integral that I started with can actually be rewritten as the integral of 1 over x minus 3 squared plus 3 dx, which is really just saying the integral of 1 over x minus 3 squared plus radical 3 squared dx. All right, and in there, that follows a very specific format. Let's see what happens here. If I let u be equal to x minus 3, then du will be just dx. And look at that, it fits it perfectly. So in other words, I can rewrite this as the integral of 1 over u squared plus the square root of 3 squared du. And at that point, I know my value of a is radical 3. And in here, because of the plus sign, that tells me right away that we're working with arctan. So it's 1 over a. So 1 over the square root of 3 times arctan of u over a. So x minus 3 over radical 3. And all of that plus c. All right. And that's what we end up with. And I guess I skipped a step here. So let's actually not skip steps. We were working with u, so the integral should be in terms of u. My final step should be replacing the u. So we have arctan of x minus 3 over radical 3. There we go. It's bad practice to skip steps like that. I don't recommend that you skip steps ever. It becomes increasingly more difficult to find your own mistakes. Now, let's do another example. So that was E. Let's check out F. And this says the integral of x minus 2 over x squared plus 2x plus 10 dx. All right. Now, in here, it's not apparent how we should start this, right? Because you might think that we should start with just a u substitution where the entire denominator is our u. All right. Now let me show you why that would be wrong. All right. So in here, I'm gonna do this in yellow, but don't do this. All right. I just want to show you what would happen if you thought it was a u substitution. And if I let u be equal to x squared plus 2x plus 10, then du would be 2x plus 2 du, right? And what that does now is my integral becomes x minus 2 over, well, I messed this up. That should be dx. Because that would tell us then that dx is du over 2x plus 2. All right. So I have x minus 2 over u times du over 2x plus 2. Now the problem with this is that these don't cancel out. This x minus 2 and this 2x plus 2 does not cancel out. And I can't manipulate this over here in any way that I can get x equals. Um, so in other words, I can't solve for x here because it's quadratic and I have the variable u on the other side. So I wouldn't be able to solve for x to somehow manipulate this in any way. So that is why we would not be able to do this with a u substitution. All right. It is very common to think that this kind of problem would be u substitution straight off the bat. So let's see what we actually need to do. So what we're going to do is the same exact thing that we did in the last problem. I'm going to start by completing the square on the denominator. So I've got x squared plus 2x plus 10. Remember, what we do is take this value right here next to the x, divide it by 2, square it, and use it to add 0. All right, so this is going to be x squared plus 2x. 2 divided by 2 is 1. 1 squared is 1. So I'm using that to add 0. So plus 1 minus 1. And then we have a plus 10. So now the first three, if I group those together and factor it, it's x plus 1 squared. Negative 1 plus 10 is a positive 9, which I can rewrite this as x plus 1 squared plus 3 squared. Now this integral over here, it would now become, well, let's see. It is now the integral of x minus 2 over x plus 1 squared plus 3 squared dx. All right. Now in here, let's do our u substitution. All right. In here, we can actually start to do a u substitution. But notice that it's a very different setup than what we had before. So what we're going to start with here is I'm going to say let u be equal to x plus 1. Now I'm doing that because again I see that here I have a function squared and I'm trying to take advantage of that function being squared here. So if u is equal to x plus 1, then du would be equal to dx. Also, if u is equal to x plus 1, then x is just u minus 1, right? So at this point, my integral now becomes the integral of, well, instead of x, I've got u minus 1. So u minus 1 minus 2 over u squared plus 3 squared du, right? Because du is just dx. And at that point, what I really have here, I have the integral of u minus 3 over u squared plus 3 squared dx, du. Now, in here, it still is not exactly what we wanna work with, all right? Because on top, I've got the u minus 3, right? I don't just have du. So what I'm gonna do here is I'm gonna use a property of fractions that I can split up fractions, right? What I'm talking about is if I have a plus b over c, that's a over c plus b over c. So I'm gonna use that real quick. And what this is gonna do for us is we're gonna rewrite this as the integral of u over u squared plus, I'll write this plus 9 over here, du, and then minus 3 times the integral of 1 over u squared plus 3 squared du. Now, notice that I wrote the denominator in different ways in each one of those. The only real reason for that is because in The one on the right, it just fits the form better of what we're going to be working with. The one on the left is going to be a very different kind of integral. Now in here, we're going to start by looking at that u over u squared plus 9. What I'm going to do here is I'm going to do another substitution. And I'm going to say let v be u squared plus 9. Then dv would be 2u du, right? And notice that I have here u du. So I can just say that dv over 2 is u du, right? And I'm going to use that to replace that entire stuff up there. In the second integral, that's already in the format that we needed to be able to integrate. So we will not be touching that, all right? We'll talk about that one afterwards. So what do I have here? What I have here now is I end up with, go back to right. So this u on top, this u du, that's going to be our dv, right? So I'm going to have the integral of dv over, what else do we have there? We have a u squared plus 9. That u squared plus 9 was our substitution, v. And then we have this minus 3 times the integral of 1 over u squared plus 3 squared du. All right. Now the integral of dv over v. All right. Oh, look at that. I missed something. This is 1/2. I replaced the u du, but it's supposed to be with dv over 2, and now with just dv. So I'll write the 1/2 out here. All right. Now, the integral of dv over v is just ln of v, of the absolute value of v. And we have that minus 3 times the integral of 1 over u squared plus 3 squared. Well, that's going to be 1 over 3 times arctan of u over 3 du, not du, plus c. There we go. That's what I meant to write. All right. So at that point, we can say these threes cancel each other out, right? The problem was not about v or about u, so let's do some replacements here. So I have 1/2 ln of the absolute value of, well, what was our v? U squared plus 9. So we have u squared plus 9 minus arctan of u over 3 plus c. And then what was the value of u? U was x plus 1. So let's go ahead and fill that in. And we end up with our final answer here is 1/2 ln of the absolute value of x plus 1 squared plus 9 minus arctan of x plus 1 over 3 plus c. And that was supposed to be a close parentheses. There we go. That's way better. All right. And that's what we end up with on that problem. So in here, notice that I used a couple of different techniques. So let's recap this problem quickly. I started by completing the square, right? That's what all this stuff on this side was. I was started by completing the square. After I completed the square, I said, well, let's manipulate this a little bit more. Let's actually try to put it in the format that we want of u squared plus the number squared, right? So I said let u be equal to x plus 1, which tells me that du is dx. It also tells me that x is equal to u minus 1. So that's what I did over here. That x minus 2 became a u minus 1. This x plus 1 became a u, right? And from here to here is just combining like terms. After that, I used again this idea of splitting up the fractions into two different integrals. And at that point, I said, well, those two integrals require different methods. One of them is a v substitution. Well, really, it's a u substitution, but we had already used the u, and we didn't want to use that variable again. It's bad form to reuse the same variable in the same problem. So we needed to do a v substitution, and that's how we ended up being able to manipulate it. All right, so that was example F. G. G says, let's take the integral of secant x tan x over the square root of 25 minus secant square of x dx. All right. So let's start by manipulating this one. All right, we wanna manipulate this, and the very first thing that I'm gonna try to do here is I'm gonna do a u substitution. I see that I have a secant in the bottom in the denominator. Well, technically a secant squared, but I care about the secant part. And on the numerator, I've got a secant x tan x. Well, secant x tan x is the derivative of secant, so that gives away what our u should be. So I'm going to start with u being equal to, well, let's make it just that secant x, secant of x. That tells me then that du would be secant of x, tan of x, dx. And notice that that's this entire part, right? Secant x tan x dx. So let's see what this integral becomes now. It becomes now the integral of, well, we just said that entire numerator is just du. So I'm going to write it as 1 over some stuff du. And the denominator, 25 minus secant squared. So that's going to be, I'm going to write it as 5 squared minus u squared, right? Because secant was our u. And at that point, that fits perfectly into the form of arcsine, all right? Arcsine. So in here, I'm going to end up with, this is going to be arcsine of u over a. A was 5 plus c, all right? And that's going to give us now arcsine of our u, which was secant x, over 5 plus c, all right? And that will be the end of that. So now let's continue. So that was G. H. H is the integral of 1 over the square root of 9 minus 2x minus x squared, and all of this dx. All right. And again, the very first thing we want to be able to do here is we want to manipulate this somehow. Um, as written, it's not exactly clear how we should manipulate it. So the very first thing that I'm going to do here is I'm going to complete the square. All right, so what I have here is really just, let's rewrite this as negative x squared minus 2x plus 9. All right, so now completing the square here takes an extra step. All right, it takes an extra step because we've got that negative there. So what we want to do is we want to know how to complete the square with that negative. So what we're going to do here is we're going to rewrite this, all right? We're going to rewrite this as, we're going to cancel, we're going to factor out that negative, but just from the first two terms, not from the last term. We're going to leave that plus 9 alone. And now from here, now we're going to use this 2, and that's what we're going to be using to add 0, right? So we're going to take that divided by 2, so 2 divided by 2 is 1, and we're using that 1 to add 0, so I do plus 1 minus 1, and then we still have this plus 9 on the outside of the parentheses. Now I want to bring this negative 1 out here, but it's inside the parentheses. So because it's inside the parentheses, anything that's affecting the parentheses should also affect it. So I'm going to distribute that negative. So I've got the negative of x squared plus 2x plus 1. Distributing that negative to this, I end up with plus 1 plus 9. So that's going to give me now the negative of x squared plus 2x plus 1. If I factor that, is x plus 1 squared. And then over here, 1 plus 9 is 10. So this is really just 10 minus x plus 1 squared. But I'm going to rewrite that even further as radical 10 quantity squared minus x plus 1 squared. All right. And again, that's just a lot of manipulation that we did there. So what this integral becomes now is the following. So it becomes the integral of 1 over the square root of radical 10 squared minus x plus 1 squared dx. All right, and in there, you should see what format this is. All right, if I let u be equal to x plus 1, then du is equal to just dx. And that was an x. There we go. So this integral now, it can be rewritten as the integral of 1 over the square root of radical 10 squared minus u squared du. And that fits the format of something very, very perfectly. It fits the format of arcsine. So what we're going to say now is this becomes sine inverse or arcsine of u over a. Our a is radical 10. But we know that the problem is never about u. So we're going to have this as x plus 1 over the square root of 10 plus c. All right, so that was h. I, let's do I. So I've got the integral of 1 over x times the square root of 1 minus ln of x squared dx. All right. So let's see what this one does. And here we go. The very first thing I see is this ln of x down here. All right, we're gonna manipulate it so that that ln of x is not in there. So let's go ahead and start with that. Let's say let u be equal to ln of x. Therefore, du would be 1 over x dx. Notice that I have a 1 over x dx there. So that 1 over x dx is going to become just du. So what we can do here is we can rewrite this now as the integral of 1 over this x and this dx. Again, just become du. And inside here, I have the square root of 1 minus u squared. And that very quickly, you can see what it should be. It is in the format of arcsine again. So what we get here is this is sine inverse of u over 1, right? Because our a is 1. And plus c, which gives me the final answer of sine inverse of ln of x plus c. All right. And again, sine inverse, arcsine, same exact thing. Um, I'm not really going to be in any way picky of which one you should be writing. J. Let's do the integral of 1 over x minus 1 times the square root of x squared minus 2x minus 1 dx. All right. So I'm going to start this in the same exact way that I did the last couple of ones by trying to figure out what u should be. All right. But in here, it's not entirely clear what our u should be. So the very first thing I'm going to do is I'm going to manipulate that quadratic in the denominator. All right, so let's manipulate that. So what I've got there is an x squared minus 2x minus 1. So completing the square here, I end up with x squared minus 2x. I'm going to divide this negative 2 by 2 and square it. So negative 2 divided by 2 is negative 1. Negative 1 squared is positive 1. So we're going to use plus 1 minus 1 to add 0, and then we still have a minus 1 out there. So what we really get here is x squared minus 2x. Excuse me, I meant to factor these first three together. So we get x minus 1 squared, that's these first three, and then a minus 2. So that was rewriting that polynomial in the inside. So what I got here really is the integral of 1 over x minus 1 times the square root of x minus 1 squared minus 2 dx, right? And in here, now it becomes clear what our u should be. u should be x minus 1. So therefore du would be just dx. And at that point, well, what do we get? We have the integral of 1 over this x minus 1 was our u. X minus 1, u. And I'm going to write that 2 as radical 2 squared. And this dx is just du. And that is in the format of arcsecant. If you answered, then try to participate. That's this isn't Dora the Explorer. Where are you going? Don't respond to me. Anyway, so this is the integral of 1 over u times the square root of u squared minus radical 2 squared. And that's going to be arcsecant. So what we have here is arcsecant of the absolute value of u over a. Oh, I forgot our a out here. So it's 1 over radical 2. Absolute value of u over a. So u over radical 2. And then plus c. So I have now 1 over radical 2 times arcsecant of the absolute value of u, so absolute value of x minus 1 over radical 2 plus c. All right, and I will leave it as that. So that is our final answer there. Let's do two more before we call it for this section. So that was J. K. So I have here the integral from 0 to radical 2 over 2 of arc cosine of x over the square root of 1 minus x squared dx. All right. So the very first thing that I see on this one is that arc cosine of x. Let's not deal with that. Let's get rid of that. So what we're gonna do is we're gonna do a u substitution. So let's say that u is equal to arc cosine of x. Then in that case, du would be negative 1 over the square root of 1 minus x squared dx. That is the derivative of arc cosine. And what we're going to do there is also figure out what our bounds should be. Because remember, if we're changing things into terms of u, our bounds should also be in terms of u. So when x equals 0, u equals arc cosine of 0. Arc cosine of 0 is 1. All right, and again, that's from the unit circle. All right, our cosine of 0 is 1. And no, it's not. Our cosine of 0 is not 1. What am I talking about? Our cosine of 0 is pi over 2. Look at that. I messed that up. Cosine of 0 is 1. Ah, that's why I messed up. Anyway, our cosine of 0 from the unit circle is it's really saying what angle do you need such that cosine is 0. Right? So such that cosine of that angle is 0. And that's why it's pi over 2. Because cosine of pi over 2 is 0. And so that's when x equals 0. When x equals radical 2 over 2, well, u is pi over 4. All right. Then I got that angle in a very similar fashion again from the unit circle. We're saying, well, what angle do we need such that cosine is radical 2 over 2? Well, that angle is pi over 4. Recall that our cosine, the range of our cosine is only between 0 and pi. In other words, the top of the unit circle, 0 to pi. All right. So that's why we would use that pi over 4 and not any angle down here. Now, what this does for us now is we can change this integral into terms of u. Originally 0, our bounds, well, now it's pi over 2. Originally radical 2 over 2, now it's pi over 4. Our cosine was our u. Look at this over here. I've got dx over 1 over the square root of 1 minus x squared. I've got the square root of 1 minus x squared, dx over the square root of 1 minus x squared here, with an extra negative sign. So what I can do there is I can say essentially from here, let's move this thing out of the way there. All right. So what I can say is from here that dx, negative du would be dx over the square root of 1 minus x squared. So this dx over the square root of 1 minus x squared is just negative du. So I have u times negative du, right? So that, if I rewrite that, that's really negative integral from pi over 2 to pi over 4 of u du. But one thing we don't really like there is the way those bounds are written. All right, we don't like those bounds like that because, well, pi over 4 is smaller than pi over 2, and we like the small values on bottom. So recall that the integral from a to b is the negative integral from b to a. So right now I've got the negative integral already, so I'm gonna just write it as the positive integral from pi over 4 to pi over 2 of u du, which gives us u squared over 2 evaluated from pi over 4 to pi over 2. At that point, when we evaluate this, we end up with, well, I write it as 1/2 times pi over 2 squared minus pi over 4 squared, which gives us 1/2 times pi over 4 minus pi squared over 4 minus pi squared over 16, which is really, well, common denominator between 4 and 16 is 16. So this is really 1/2 times 3 pi squared minus pi squared over 16. That's the, where did I get the 3 from? I skipped a step in my head. That's what happens. All right, 4. 4 pi squared minus pi squared over 16. And then 4 pi squared minus pi squared is 3 pi squared. So I end up with 3 pi squared over 32 as my final answer. All right, now let's do one more. All right, we're going to do one more, and then we'll call it. So I think it's example L next, right? Yeah, L. So example L, we've got the integral of x over the square root of 9 plus 8x squared minus x to the fourth dx. All right. The very first thing that I see there is we don't have a quadratic on the denominator inside the square root, which is different than all of the other examples we were just doing because they all had a quadratic in the denominator somewhere. Well, what I'm going to do here is, well, I see that it is in quadratic form, right? By that I'm talking about, look at the exponents of that denominator. I've got 4, 2, and none, right? That's quadratic form because this exponent is double this, right? Which is 2 more than the previous one. So what we're going to do here is we're going to start by making a very simple u sub. And we're going to say let u be equal to x squared. If u is equal to x squared, then du is equal to 2x dx. So in other words, du over 2 would be just x dx. And I wrote it that way because we have an x dx on the numerator. So at that point, I'm going to say, well, this becomes the integral of, again, this x dx becomes just du over 2. So I'm going to write it as 1/2 times du. Inside here, we have 1 over the square root of 9 plus 8u minus u squared. All right, notice that u squared would be x to the fourth, right? So now that we have that, I'm going to manipulate this next statement that we have there. All right. So what I'm going to do there is I'm going to rewrite this using completing the square. So what I have here is I've got negative u squared plus 8u plus 9. And again, we're gonna factor out that negative because when we complete the square, we don't want any leading coefficients. And I'm only gonna factor it out of the first two, leave the 9 alone. The next thing I'm gonna do there is I'm gonna use this value in front of the u to add 0. So I take negative 8 Negative 8 divided by 2 is negative 4. Negative 4 squared is 16. So I'm using that 16 to add 0. Notice that plus 16 minus 16 is adding 0. It doesn't change a thing in our problem. But now, I want this negative 16 to be outside of the parentheses. So what we can do here is distribute the negative in front so that it can actually get out of there. So we have a plus 16 plus 9. At that point, I can factor these first three terms. So I have negative u minus 4 squared plus 25, right? 16 plus 9 is 25. I'm going to write this as 5 squared minus u minus 4 squared. All right, now why would I want to do that? Because now I can rewrite this integral now, and we have it as, well, we still have the 1/2 integral of 1 over the square root of 5 squared minus u minus 4 squared du. All right, in there, I have that u minus 4. Don't like that. I don't want to have it that way. I want to manipulate this more just so that it actually has the exact form of one of the things that we had before, like one of those first three integrals. So what I'm going to do here is I'm going to make another u substitution, but I'm not going to call it u. I'm going to call it v. So in here, I'm going to say let v be equal to u minus 4. Then dv is just du. And what that does now is it allows me to rewrite this integral as 1/2 times the integral of 1 over the square root of 5 squared minus v squared dv. And now that is clearly in the form of arcsine. All right, so I have 1/2 times arcsine of u, well, in this case it's v over a, our a is 5, and then that plus c. But the problem wasn't about this v, all right? We had no problem with the v there. What we had originally, the problem was about, prior to that, it was about u. So I have 1/2 sine inverse of, and instead of v, we're going to insert a u minus 4 over 5, and we have that plus c. But again, the problem was not about u, right? Before the problem was about u, what was it about? It was about x, and u was x squared, right? So what we're going to do here is we're going to rewrite this now as 1/2 times sine inverse of x squared minus 4 over 5, and that plus c. And now we're done. Now we're done with that section. And that is the end of 5.8. 5.8? Yes, 5.8. Yes. All right.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.